Recording in progress. Hello, everyone. I can't hear you if you're talking. Gee, somebody's talking. I can't hear. All right, poll is closing in 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And these are the results. And this is the result. So it's a sealed seal. It's sealed. You see the point? Yeah. Sealed.
What is it? Is it the brain?
I think so. Kind of looks like a brain. Yeah.
Well, I hope nobody ate it after it was scanned.
Well, I don't know. I didn't keep it. Somebody else took it. Actually, there's a few interesting things to see here. First of all, you notice that it's very good contrast between gray and white matter. This is the white matter and this is the gray matter. And what type of scan is this?
T2 weighted.
No, so it's T1 weighted. And if I'm not mistaken, yeah, actually, yeah, it's T1 weighted. However, I think due to asphyxiation, the gray matter doesn't look great as opposed to what it looks for humans. So, which is interesting. This is a dead brain, and so it's, I don't know what they put in it, formaldehyde, or I don't know. Pick your tissue asphyxiation type of thing. However, there's interesting things to see here. Do you notice the ventricles? These are the ventricles. And you can kind of see all those holes, but do you see that they have kind of like a structure, kind of like a, I don't know, and there's a little bit brightening next to them. Any ideas? Any ideas what these could be? Like what causes this?
Are there arteries, blood vessels? No.
What they could be, but that would not result in those type of artifacts. You see, this is a big one. Here's a big one, big artifact.
Is it at an air interface?
That's right. Air tissue interface. So these are susceptibility artifacts because of air tissue interface. Absolutely. So it creates a very strong T2 star effect next to, very close. And then as you move further away, the T2 star effect is diminished, but there is a little bit of course, of shift. Remember, the effect of off resonance is either T2 star, there's some shift that is associated, and that shift results in some brightening because when you have signal that is moving and it moves on top of other signal, then you get this brightening effect called pileup. And that's why it's a little bit brighter on the bottom. And if we looked at the phase map, then I think you would definitely see significant phase distortions because of that. But I don't have the phase maps here. But it's a very common artifact when you have air tissue, because this brain is dead. Then you know, the ventricles are pretty much empty, and so they're filled with air, and so are all the pieces here. And I think there's actually a cut in the brain here. They made a few cuts. As you actually see, there's a cut here, and then there's a cut here. This is a 1-year-old seal that died because of epilepsy.
It's that red tide thing. Sorry.
Pardon again?
Too loud. Sorry.
No, it's okay.
It's like, that's the seal that Ben scanned?
Yeah.
And it had like red tide or some kind of toxicity.
I don't know. But yeah, this is Ben's seal brain.
Yeah,
Absolutely.
that morning smelled really bad in the BIC.
Oh yeah.
Yeah.
Okay. Well, now it's sealed. It's a sealed seal. So we didn't smell anything, which was good. Okay. Any questions about the seal and about the brain? But it's interesting actually to see the structure of the brain. It's very different, right, than the structure of the human brain. I mean, there's familiar stuff, but then it's also very different. So, like all that stuff over here. It's pretty big. Yeah, I also is oriented a little bit differently than like it's kind of like almost 90-degree rotated. You know, the brainstem actually comes in there from a different region. I can actually show you that one if you're interested. You're interested? How much you're interested? Like very interested or a little bit interested? It's not that enthusiastic, I have to say. Let's see. Let's see. I think we do it this way. 3D volume rendering. Rotating that thing. Yes. All right. Oh, I'm not sharing it. I'm just looking at myself, I guess. Hold on. Let me share. You see it? This is the 3D volume rendering. And I'm just going to rotate it. You see the two hemispheres. And yeah, I mean, Ours, stem actually goes down from here, but the seals goes, backwards, So it's kind of strange. And I can do, of course, all that other stuff that the cool thing to do is like, cut and, Da-da-da. Isn't MRI so amazing? What can I say? Right? Oh, and actually, oh, did I close it? Okay. All right. Never mind. Let's see. Move here. Okay, so where were we last time? Fast gradient echo sequences. We talked about steady state free precession, balanced SFP, the case where we just do a flip angle minus flip angle, flip angle minus flip angle, and make sure that all the gradients are fully balanced and sum to zero. Then we looked at the case where we try to crush the magnetization with a gradient, but it turns out that magnetization does what it does and doesn't want to be really crushed, but to be averaged across all possible steady states of SFP. And then finally, we did also RF phase cycling. And when you do RF phase cycling, then you actually are able to crush the magnetization appropriately and then end up with pretty much a very fast, rapid, purely T1 weighted acquisition, which is extremely useful for contrast imaging when you want to look at contrast. Right? So then we looked at the case of RF flip angle and phase, RF flip angle and phase, and their effect on imaging. And we saw that the behavior is quite complex. It's not, linear. Like the signal doesn't necessarily increase with flip angle. It increases for a certain amount of flip angle, depending on the sequence, but then it starts dropping down. And of course, you want to optimize, your contrast, and you want to optimize the SNR, both of them, somehow in a good weighting, such that you'll get an image that will not be noisy and will also have good contrast between the different tissues. Any questions up to here? I also send you in Piazza a really nice reference for a review paper from almost 20 years ago, actually, that describes some of these rapid pulse sequences and how they're actually being used. And it's a really good summary of these pulse sequences. So I highly recommend reading it. Okay, maybe we can add that to the homework.
Sure, yeah.
Okay. All right, so the next thing that we're going to look at is the dependency on timing, TR, and TR, which is how fast we repeat things, and also the echo time, and see how these are affecting our image contrast. So there's a lot of echo time considerations. Okay, so what happens when you have the longer TE? What type of weighting do you think you're going to get if you have a longer echo time? For gradient echo sequences, not for spin echo.
T2 star.
Yes, absolutely. So you'll get more T2 star weighting. So for example, this is very typical for bold fMRI. So blood oxygenation dependent, level dependent signal, where deoxygenated blood and oxygenated blood has a different susceptibility. And so deoxygenated blood has actually different magnetic susceptibility in tissue, which causes signal dephasing next to these blood vessels. And of course, perfusion of blood into the tissue may also affect that. So some consideration, for example, for longer T would be either do a bold or a T2 star weighted perfusion in perfusion type of imagery. Okay, now if you actually want to do short TE, so consideration for short echo time is to reduce flow and motion sensitivity. Once you excite and you have spins that are moving, that can cause all sorts of things to happen. For example, spins are moving while your gradient is applied. That means that spins are not going to accumulate a linear phase over time. They're going to accumulate a phase, but that's incrementing because they move. They see actually a slightly different gradient as they move through. So that can cause signal dephasing and other sorts of artifacts. So short TE is often done to reduce flow and motion sensitivity. And this is, by the way, one of the reasons that spiral sequences or radial sequences are much more robust to flow, because immediately after RF, you acquire the center of K-space and then you go out. So your echo time is very, very short. It's sub-millisecond, whereas in Cartesian acquisition, you have to first move in K-space and then come back in K-space. So that can cause some issues. In particular, if we look actually at the pulse sequence diagram, then you have, let's say, the RF, and then you have GX and GY, and for spirals, you immediately start collecting data, right? So your echo time is often defined as the time that you cross the center of K-space, which is actually in the beginning. Whereas in Cartesian acquisition, right, you apply the RF, but then you have, phasing code, and then you have also the readout. And then your echo time ends up being here. And so you get more sensitivity to both T2 star as well as motion sensitivity. Anyway, so the notion is that you actually have to go out in K-space, right? And then collect this line. And then you go out in K-space and collect the second line. So the time that you cross the center of K-space takes a long time. And the idea is how to shorten it, even for Cartesian. Let me give you a hint. Remember that we said that images are approximately real? They should be real, right? And so K-space has some conjugate symmetry or approximate conjugate symmetry, right? So how can you use that in order to reduce your echo time?
You just start in the middle of K-space and then just take half.
Yeah, so you can actually, instead of going all the way here and then collecting this line, I can actually just go straight up and then collect half of this line, right? And then straight up and collect half of it here, and straight up and collect, and then my echo time will be much shorter. Okay, because I don't have to wait till, all of that. That is sometimes an issue though, because to be honest, the image is not completely real. So what people actually do is they move a little bit that way and collect, and then move a little bit and collect. And so they get a little bit of the left side such that they can estimate some phase and then correct for it for that slow changing phase. And this is called a partial readout echo, right? Partial readout. And it's a very common thing to do with angiography, because again, with angiography, remember, the blood, you're trying to image blood and blood flows. And so if you want to reduce your sensitivity to flow, you do a partial echo. Very, very common. And then if you really want to get stuff that has a very short TE, short T2 star, then that's another way of capturing it using this partial echo. Okay. Of course, you can also do radial acquisition and other things like that, but that's a very common thing to do. And scanners will have an option to have a partial echo, and you can tell the scanner if you want 70%, how much partial the echo should be, 60%, 90%, and then your TE can change. The reconstruction, of course, if you want to gain back the resolution that you lost because you didn't actually collected this part of K-space, then you have to perform some reconstruction that compensates for that. And this is one of the algorithms. It's called homodyne reconstruction, but it's beyond actually this class. Might talk about it. Any questions? Okay. The other consideration actually that we have for echo time, and it's also one of the options that you'll see on MRI scanners that is very, very common. And let's see, I actually had my MRI scanner window open, but it might have closed, which kind of sucks because I wanted to show you because it's kind of cool. So let's see if I can actually open it up again. Okay. Go connect to server. There you go.
I think someone might be scanning though. Are you?
Oh yeah.
Yeah, I think it's like booked.
Okay. All right. Well, next time. I'll show you then the next time. Let me then share my. Am I sharing my screen still?
Yeah, but there's something covering the screen. Okay, now.
Also now?
Yeah, it's good.
All right. So the other thing is actually related to fat and water imaging. We kind of talked a little bit about it, but sometimes you want the fat to be with the same phase with the water image, and sometimes you want it to be opposed phase. So that's another consideration, especially if you want to also be able to separate fat and water. You want to be able to image it multiple echo times in order to then use the fact that fat has a different resonance frequency than water in order to be able to separate them. Right? So either you want to have it in phase or out of phase. That's for water. And then Dixon imaging is called, it's an algorithm in order to be able to use those images of in phase and out of phase in order to separate the fat and water, to separate the images into a purely fat image and a purely water image. So here's actually how it works. Here's how it works. After you apply an RF, okay, like this, hold on, yeah. So this is an example of a breast image, and this is actually a post-contrast acquisition. So you could see here, there's actually a tumor, and the tumor is enhanced because of the contrast. So it's a T1 shortening, and this is the fat image, and you see how bright the fat is, and it actually can obscure your ability to see the tissue. So it's really important to be able to separate between fat and water. Now, after excitation, fat and water will be have exactly the same phase, but then over time, they'll accrue different amount of phase. The water will accrue some phase because they're usually not perfectly on resonance, like not everywhere in the image, right? It will be exactly the same. So they might progress a little bit, but relatively slow, while lipids have a resonance frequency of about 3.5 ppm away from water. So at 3 Tesla, we're talking about 460 hertz. So that's quite a bit. So very quickly, within I don't know, 2 milliseconds or so, you get like opposed phase. So what you'll get then after a certain amount of time, the fat and water will have opposing phase. And then if you actually collect and apply a readout gradient that it reads out at exactly this time point, then your image is going to be weighted by, it's going to be mostly manifested by this particular phase. Okay, so at this time point, the fat and water will have an opposed phase. So if you create an image by repeating this experiments over and over again, but have exactly the same echo time, and of course you add phasing code and so on and so forth. But since the echo time is here, then you'll get an opposed phase. Now, if you let the delay the echo time even further, then there's going to be at some point where fat and water will get back to exactly the same phase, where fat completed the whole cycle with respect to water. And so if we actually create an image or an echo at this time point, so that would be the gradient, and then this would be the echo time, then we'll get an image which has fat and water exactly with the same phase. Okay, and you can do that in the same TR because there's often enough time to do that, and so you can have multiple echoes, right, with the same TR. So you don't necessarily have to lengthen the acquisition significantly. What you do basically is you read K-space, you go out in K-space, you read one line, and then you read the same line on the way back, for example. And that gives you the opposed phase. Or alternatively, going backwards can be sometimes problematic. So what you do is you rewind it, and then the second echo collect in the same direction, okay, on top of it. And then the next time you excite, you do the same thing, but for the second line, and so on and so forth. So you'll get two images out of this acquisition. This is an example of an in-phase image of the abdomen. This is the liver, for those who do not recognize. I believe that this is a piece of a kidney, and these are the bowels. That's subcutaneous fat, and this is belly fat. And then this is an out-of-phase image. Okay, this is an in-phase image, and this is an out-of-phase image. And what you will notice, actually, I don't know if you know this, but your kidneys are embedded in fat. Did you know that? There's a good reason for this. It protects the kidneys because it's kind of like raw, right? So it protects it from, kidneys are a very sensitive organ. I don't know if you ever watched Grey's Anatomy or House, all these, right? When they have to rush in with the kidneys, and very, they handle them very, they hold them and then they stick them in the person, so, trying to sew him back, all that kind of stuff, right? So kidneys are very sensitive. So they're embedded in fat. And here's an interesting thing that we see here. Because it's embedded in fat and this is opposed phase, then there's actually a line surrounding the kidneys. Because at that point exactly, you have fat, the same amount of fat and water in the same voxel, and so their signal cancels. Okay, so there's going to be an area. So you see these contours. Also, you see a contour here. You see a contour here? Yeah. Anybody has an idea what is this?
It's an
Unrelated.
artifact.
An artifact. An artifact coming from what?
Aliasing.
It has this shape. So it's actually aliasing of this, and this is probably what's called parallel imaging. So this was accelerated using parallel imaging. We'll talk about a little bit later. But if you accelerate then sometimes you might get residual artifacts. And this is a very typical residual artifact. This is, by the way, another artifact coming from this aliasing over here. Okay. You see the flat thing is very similar to here, the edge. This is also fatty, you see here, compared to here. So that allows you to distinguish between fatty lesions, for example. If you there's a lot of, for example, benign fatty lesions in the liver, and in order to diagnose that is actually a benign lesion, what you'll go and do an opposed phase acquisition, and then you'll see the contour and you're like, oh yeah, that's sure, that's fat, not the problem. No need for intervention. But if it's, let's say, a malignant tumor, then it won't have that. Now you can take those two images and do what's called Dixon imaging, and be able to then pretty much it's not exactly the same, but if you add these two images, this is in phase, this is out of phase, you add these two images, you get the water image, and because these are opposed phase, if you subtract them, you end up with a fat image. Saying that, this is not exactly going to work out, because in addition to that, don't forget you have off resonance. So just adding and subtracting doesn't necessarily give you what you want. And so you have to correct for the field inhomogeneity in order to be able to do this. So often actually people acquire 3 echoes, not 2. Although now there's very successful imaging algorithms called 2-point Dixon, which basically uses just 2 images. But you have to kind of estimate what is the background field for that. Any questions? Okay. All right, so here's our 2 images, gradient spoil images. Which one is opposed phase and which one is not? This is the abdomen, coronal scan of an abdomen. Anybody wants to give a go?
Is it the right?
Who said that?
All
right.
Space.
How do you know that is the right?
I'm just looking for like right around the, I don't really know how to point to it. I'm just looking at for the, like, that's one spot, but kind of move to the right a little. Or, and up a little, it's a difference between.
Yeah, you see contours, right?
Yeah.
Basically, when you see contouring around tissue, definitely the fat is usually brighter in T1. Then if you see contours, then that means that it's opposed phase. By the way, also because the nothing. Ignore just what I said. The other thing that so here you see all the contouring, and so that's very nice. Let's see if so if you actually look at those arrows, then you see this is the liver. The liver, although it has fat, but the amount of fat in the liver is about 5% for normals. So it's not a huge amount. So it's around, this is more visceral fat, I think it's called. And you'll see that there's, this is because this is a, what is called? This is in phase, so you don't see any difference. And actually there's a diagnosis here. So left adrenal lesion, this one, with signal lost in the post phase. So there's a signal lost in the post phase compared to in phase. And also it has kind of a contour around it. And the reason that it loses phase in the opposed phase is because this particular lesion has both fat and water in it. And so when it's opposed phase, then you got like, cancellation within the voxel. And so you get loss of signal, whereas in phase, it comes back. Remember, the in phase actually is after the opposed phase. First you have opposed phase, then you have And so this is suddenly, getting brighter, which is kind of surprising, right? But it kind of makes sense if it's made out of fat and water. So that makes that a benign lesion. And so that's not a problem. Okay, so this is one way to diagnose this. MRI, so amazing. Right, think about it. Let's say you decide to pick a field like, I don't know, X-ray or optics or something like this. I mean, you can do all that stuff. I mean, to be honest. What can you do? More light, less light? I don't know. All right. So the last knob of contrast that I want to talk about is preparation sequences. And the argument here is, this part of the imaging can have a very short TR, very short time repetition, can be done very, very quickly, right? So maybe we can do something to prepare the state of magnetization before, and then do a series of acquisition such that the state that we prefer will be maintained for a certain amount of time. So it's kind of like a pseudo steady state. And then we'll collect, as many phasing code as we can. And then we'll do another preparation. And then, immediately go like collect more phasing code very, very fast. And we're not going to rely on the inherent contrast of graded echo sequence, but really use the preparation in order to really get the contrast that we're interested in. And we're going to use the gradient echo part just to do the fast imaging, because we can pretty much knock these spins pretty quickly. Okay, so these are called prep sequences. So there's a lot of preps, and we actually talked about some of those preps. For example, can you give me an example for a prep that we talked about?
Doing an inversion to like suppress a certain type of tissue.
Right, inversion to suppress a certain type of tissue. So for example, kind of inversion recovery to suppress fat or to suppress fluid that we saw before, right? So that's one example. Okay, so often we'd like to do fat saturation. That's very common thing to do, to saturate fat. And fat can be saturated in many different ways through inversion recovery. That uses the T1 property of fat, right? But we can also do a frequency selective RF pulse to only select the frequencies, away from resonance where actually fat resonates, right? So in 3T, it will be 460 hertz away, so we can create an excitation that only excites fat. And we excite fat with a 90 degree, and then we kill it with a crusher. So we put a very large gradient that dephases the signal from fat. And then we do a water excitation, or just a regular excitation, a series of regular excitations. And then we'll only excite water because fat has been saturated. This is called fat saturation. Okay, that's one example that is very typical to do. Or you can leverage the T1 shortening of fat, the short T1 of fat, in order to do an inversion recovery type. And depending on the field, then you want to apply one or the other. For example, in low fields where the frequency between fat and water is actually not very far, then you'd want to maybe rely more on T1. But for higher field, it's very easy to separate between fat and water because they're so far apart in terms of the resonance frequencies, right? Because it's really field dependent. We're talking about ppm shifts, so it's really always with reference to the resonance frequency. So at 7T, I mean, we're talking about a kilohertz away, right? That's really, really far. So very easy to do water excite, for example, or fat suppression in 7T, except that you also have field inhomogeneity. And so that could be a problem, because let's say you have a linear variation in the field and you try to separate, like excite fat, and you excite at 460 hertz, let's say away at 3T, but you might then saturate water, which are off resonance at some other places, right? So there's always trade-offs there. Other things that you want to do is to do myocardial tagging. You can do tagging pulses to tag the myocardium, and people have done things like, for example, if this is the heart, like a cross section through the heart, this is the this is the heart muscle, and here is the blood. Then there's actually a way to create a grid of black lines along the heart. Sometimes it's done in 2D, sometimes just in 1D. And when the heart contracts, and you can see the distortions of those grids. Can you see actually what I drew here? After the heart contracts, you can actually see the distortions of these cubes. And from that, compute stress, for example, of the tissue. Okay, so there's this is called SPAM, a SPAM preparation pulse. Your TA is actually an expert in those type of pulses, but for other uses. Finally, you have T2 preps. T2 preps are if you have certain tissue that you want to emphasize the T2, you can actually do a series of pulses that prepares the magnetization, to be sensitive to T2. And then after that, you just very quick gradient echo. Remember, for T2 weighting, you have a very long TR, right? Because if you want to have pure T2 weighting, you have to excite, you have to wait 80 milliseconds or so. You have to have a spin echo, right? If you want not T2 star. And then after 80 milliseconds, you do a readout. And then now you have to wait till the magnetization recovers completely. That is very, very slow. Okay, so we're talking about very long TRs and very long TEs. It's not very efficient. So what you could do a sequence like this. You do in 90, and then you wait, and then you do a minus 90. Okay, what happens there? You excite magnetization. Magnetization then starts decaying with T2, and then you put it back into MZ. So if you look now at this is the Z direction, this is XY, and then if we look at the magnetization, it's being tipped, and then once it's being tipped first, and then let's say this color is a long T2, so it stays long, but then the blue is a short T2, so it actually decays. And then you do a minus 90, and now you've got yourself, after the minus 90, you got your magnetization kind of looking like that in MZ. Okay, and now you can do a gradient echo sequence. And if you just do a few of these TRs, then most of your contrast will actually come from the differences in MZ originally. Okay, so that's one way. This is very subtle here, but actually it's not going to work if there's off resonance, because nobody said here, oh wait, what about this is really T2 star, not T2, right? So if you really want to do it, you actually have to put a spin echo here as well. So another 180 actually here, and then that's going to work. Okay. All right. Okay, so this is T2 prep. And then magnetization transfer, that's another type of a preparation where you apply an off-resonance RF pulse, which is very, very strong. And that actually creates transfer magnetization from water into protein structures, large molecules. And so you can actually get a reduced signal of the water because of this exchange that happens. And so it's a very typical preparation that you apply a very strong RF. It cannot be described by block equations, for example, but for example, Cindy here is from a group that does a lot of this magnetization transfer in another method called CEST, chemical exchange saturation transfer, that leverages these very powerful RF that actually excite spins in proteins, and because water molecules exchange with those spins, then you've got saturation of the water pool. So that's another way. And so here's a typical way of doing things. You do some magnetization preparation that stores your contrast in MZ. Okay, now the contrast is stored in the Z direction after that. And then you do an imaging sequence immediately after. And then after that, you do another magnetization preparation, you repeat, and so on and so forth. And you try to squeeze as many of these as you can, although, of course, your contrast would actually change as you do this, because, things will start recover and, so on and so forth. So this is always a trade-off of how often to repeat the preps and how much lines to acquire. This is always engineering things. Any questions? Yeah, light, who cares? All right. Oh. Do you hear the sound? I can listen to this all day long. I can listen to this. It's great. But what you heard is like, right? So the that tone comes from the TR, like how fast these are happening. And then mag prep, mag prep, mag prep. And that's why it sounded like that. Okay. Otherwise, it would have just sounded like, right? Like it's just the TR. But no, because you have these preps, it sounds like, You want to hear it again? So nice. I mean, I bet you, Eken, that song would have won the Eurovision. I bet you.
For sure.
For sure. We should submit. Okay, so here are just some example. I showed you this before. That's non-fat. That's without fat saturation. This is what with fat saturation, right? I showed you this before. This is a balanced SFP sequence. This is a 4-chamber view of the heart. And then on the right, what you do is an inversion recovery. Okay, so you invert, and then so what you do is based on the RR cycle of the heart, you trigger the inversion. So let's say now you've got a trigger, so the heart starts contracting, right? Then you do an inversion. And then immediately after you do the inversion, you start performing imaging. And what happens is that while you're collecting those images, fat starts recovering. You see, fat starts recovering. And kind of the contrast actually changes within the cardiac cycle, because the way you do it is, like you have this is the heart. And then basically you do here a prep. Here you do a prep, and then you collect, and then you do a prep, and then right, and collect data. And then each one of these, so for the first, let's say for the first cardiac cycle, you collect the first phasing code. For the second cardiac cycle, you collect the second phasing code. For the third cardiac cycle, you collect the third phasing code, and so on and so forth. So now, effectively, you can create an image at this point, and at this point, and at this point, and at this point, because the heart is repetitive. And so those images that you see here are basically images with an inversion after this, and this is why you can see this video, and you can see how the contrast actually changes. Fat is inverted, and then goes through 0, and then becomes brighter at the end because it recovers, right? And then in the beginning, actually, the myocardium is very dark compared to the blood, but then after that, it gets back into its own, steady state. Okay, so you can very nicely see the effect of the prep. And of course, if you wanted to get the contrast to stay the same, so you can actually you will have to repeat the prep many faster, pretty much, because 1 second is actually too long to repeat the prep. Does that make sense? Does anybody understand this actually acquisition? So you do this is like the first phasing code is acquired, you just acquire just the same phasing code over and over again, and then the next you acquire the second phasing code over and over again. So basically, for each cardiac cycle, you've got the same phasing code, but different times after the the trigger. And so then you collect, the first phasing code from the first cardiac cycle at the beginning, and then the second phasing code from the second cardiac cycle in the beginning, and you build an image out of that, assuming that the heart is periodic. Okay. So that's why we get a lot of images. Basically, we get an image for every time here. But then we need 250, cardiac cycles in order to finish an image, right? That's a lot of cardiac cycles. So you have to do a breath hold or a long breath hold. I don't think anybody can do 256 cardiac cycle breath hold unless the heart rate is, really fast. Can you do how many can somebody hold their breath for a minute? No? Okay, well, I think I can do 2 on a good day. Yeah, maybe 2. So happy to be a subject for any of these studies for breath hold if you want. If you want like a really nice picture for your paper. All right. Okay, just to summarize, there's a lot of things that you can do in order to control the contrast. You can actually do different type of spoiling, either not spoil with gradients or spoil with RF. That gives you completely different images based on what you do at the end. RF and flip angles, those control also the contrast, and depending on the type of sequence, they'll emphasize, for example, gray and white matter differences and so on and so forth. Finally, you have control over the TR and the echo time. That you can use for fat water separation, for T2 star sensitivity, or insensitivity, and so on and so forth. And then finally, use preparation sequences. In your homework, you'll have a nice prep. What kind of prep they're going to make?
I think for flow imaging.
Okay, a flow
Or
prep.
flow prep, yeah.
And what about the B1 prep? No, we didn't give it this time.
Not this time. We can,
give
but
you-
I think maybe late in the next one.
Next homework will give you also a B1 prep, so you could prep your magnetization such that it'll be sensitive to B1. Okay. All right. Yeah, just a little bit about names. So RF spoiled sequences have many names. Very common is SPGR on GE sequences, or Flash on Siemens, and I think T1FFE is for is Philips. Balance SFP is called TrueFisp on I think Siemens. Fiesta, that's the GE version of it. Gradient spoiled, Grass is one of them, or GRE, that's GE. Grass, I think it's Siemens, and FISP is Philips. So vendors are, the point is vendor acronyms are really confusing. So really, if somebody tells you something, just ask what type of sequence really it is. They're gonna say, oh, just try Fiesta. And it's like, what is Fiesta? Well, what's Balance SFP? I was like, oh, okay. And then if you want to go to the acronym, go to mrtip.com. There's a lot of acronyms there, and then they'll go and describe those. So I stole a lot of these slides from a lot of people, but in particular, Brian Hargreaves, who's teaching, by the way, an advanced class on MR right now at Stanford's, which I think you're welcome to also audit. So if you want information, I can post that information on Piazza. I think they'll be very happy to do that. All right.
Yes, Brian mentioned that they welcome everyone from all over the world to audit the course.
There you go. Brian is Canadian. That's why he's very nice.
But so is Dan.
There you go. So 2 Canadians teaching a class. Well, I mean, like, think about it, how great it is. Okay, so the next topic I want to start covering, and I think we're going to end in about 13 minutes or so. We're going to end a little bit early today. Is a very important topic. Actually, extremely important topic. How important?
Extremely.
Extremely. Off-resonance is very important, but SNR is extremely important, because without SNR, you can't really do anything. Like you could devise your most amazing sequence, like do all sorts of sensitivity, but if you don't get the signal, then it doesn't really mean anything, right? Like if you cannot overcome noise. So there's many definitions of SNR. If you're an EE, usually it's not the one that I'm going to describe right now. But this is a very typical way of evaluating SNR for MR. And basically, we're evaluating SNR by looking at the signal amplitude divided by the noise standard deviation. Okay, that's how we're going to define SNR. We're also going to define CNR, which is the contrast noise ratio, contrast to noise ratio, which is really the signal difference between 2 tissues divided by the standard deviation of noise. And why is that important? Because let's say I have blood tissue that has that much SNR, and I have that much signal, and then the noise, what color should I use for noise? White, because it's white noise. Then this is the noise level, right? So the noise actually modulates, you know, our signals a little bit, right? So that's a good signal to noise ratio, right? But let's say I have a sequence where I also want to look at muscle. What's the color of muscle? It's pink. Pink is good color for muscle. And let's say now muscle has also very good SNR. And its signal is slightly below blood. So yeah, both of them has great SNR, but the problem is that the CNR here sucks, because the difference between the blood and muscle is such that the noise really overwhelms that difference. It's very hard to distinguish. Okay. So here's another situation where you've got actually quite a bit of noise. And then let's say this is, what did I say? This is blood, and this is muscle. Muscle is almost drowning in the noise, but it's a little bit above noise. But now the contrast to noise ratio is quite large, so you'll be able to see very well distinguish between the blood and muscle. Okay, so which situation is advantageous? Well, like everything in MR,
It depends.
thank you. Thank you. It depends, right? It depends on the application. Okay. So from a so let's talk about SNR consideration. So first of all, there's these physical and instrumental ones. You actually have dependency of signal to noise ratio with your B0. So the higher the field, the more magnetization that you get, and hence the SNR is improved. Okay, maybe, but potentially it's improved. And this was the race for high field. That's the premise. You get more SNR. So people went from 0.3 Tesla to 0.5 to 1 Tesla, 1.5, 3, and 7. And now there's other places that have 10.5 and 11.7 or something like this, right? Very high field in order to get that SNR. The other thing is the coil geometry. So the fact that you use coils and their geometry may also affect your ability to pick up the signal. Definitely, if you have a large coil that's far away from the body, you'll have much lower signal to noise ratio from a small coil that's closer to the body. Okay, but they'll have a very different coverage. So we'll talk about that a little bit more a little bit later. So the geometry of the coil is important. In addition to this, actually, the type of coil that you have, for example, its conductivity may affect the signal to noise ratio. So if you use a coil from a crappy conductor, you have a lot of resistance, and that will cause losses and potentially more noise in the image. But also the sample the sample that you image itself may also be conductive. And is that true for humans? Are we conductive? Unfortunately, yes, right? Because we can get electrocuted, means that current will go through us. But at the same time, heart, kind of works that way. And, there's other things that are really useful in order to do conductivity. For example, the fact that I'm moving my hands, there's, electrical signal moving from here to there and back and so on and so forth, right? So that's important. But that can also cause noise in the image as well. So the sample itself may actually generate noise. And then we have a whole chain of coil to amplifiers and digitization, and they all have what's called a noise figure, like how much noise is being injected into the system, and that is also affecting your signal to noise ratio. Could affect. Now, in a well-designed signal, you try to have that not affect, okay? But or to be the least least affecting, such that it's negligible, and we'll talk about that a little bit more. So this is the physical and instrumental sources of noise and where they can come. The other are basically imaging sequence dependent. For example, how much time you spend collecting data. I mean, that can actually have a huge impact on SNR. If we spend more time collecting data, then maybe we'll collect more signal over a certain amount of time. So you'll have much better SNR efficiency there. The resolution is very important. Think about that. If I look at my entire body as a single voxel and I excite it, all my spins in my body are going to emit a signal together. That's a resolution of 6 feet by, 2 feet by 1 feet cubed. That's pretty big voxel, like me, right? I'm a big voxel. But the SNR would be amazing, but the resolution sucks. So then I can go lower resolution, and then the lower I go, the finer resolution I get, the less amount of spins that I will get in each voxel, and hence my signal to noise ratio is going to be reduced. And so resolution is a very costly, actually, source of noise. It's not really a source of noise, but it's a result, right, of having less spins. The timing of the sequence are very important. For example, relaxation. If I wait too long, I'll get T2 star waiting, T2 waiting, and all of these will cause my signal to decay. So that can be an issue, especially if I try to do all sorts of preparation sequences and stuff like that. The flip angle is going to have effect. We saw the effect of the Ernst angle, right? Like that optimizes the amount of signal. So signal to noise ratio. And finally, the K-space coverage. So how do you cover K-space? If you cover it on a Cartesian grid, or you cover it on a polar grid, or you cover it on a spiral grid, all of these has slightly some effect on also your signal to noise of the image itself. Okay. So all of these are many considerations that you want to consider when thinking about SNR. So let's now look at noise sources. Okay, and I'm gonna hand wave a little bit, and we're not really go into very sorry about that.
Bless you.
Thank you. We're not gonna go too deep into this, but I'm just gonna give you an idea of what are the sources. So MR, you can pretty much assume that the noise is really Gaussian and additive. And this is really true because the source of it is really just resistive noise, okay? And it's basically due to Brownian motion of charge carriers, either electrons in a coil or electrolytes in the body that move randomly and create noise, okay? So that's pretty much the source. And the noise then is Gaussian. That is not true, for example, in optics or other regimes where noise can be Poisson. And then often people approximate it as Gaussian. No, MR signal is really corrupted by Gaussian noise. Now, it doesn't necessarily have to be white Gaussian, but it's definitely Gaussian, right? To a very good approximation. It's a really Gaussian, it's a true Gaussian process. So the noise is a function of frequency is pretty much white. It's 4 KTR. And KT is this is Boltzmann distribution. T is the temperature, and R is the resistivity. It's the typical white noise where the standard deviation is basically the square root of 4 KTR times the bandwidth. So if you have a filter, then basically the bandwidth of that filter will then determine also the amount of noise.
Hey, Vicky.
Yep.
So N of F, when you say noise, you mean noise
As a function of frequency.
Noise, power, spectral density.
Yeah, noise power. So it's pretty much white Gaussian.
It's like volts squared per hertz, right?
I believe so.
Yeah. Okay.
So if you actually have, here's a good model. Okay, this is our body, and our body has electrolytes that actually have also random walk, right? Brownian motion. You have a coil that is inductively coupled to the body and will pick up signal that comes from the spins, but it will also pick up any induction due to this Brownian motion. After that, you have a preamplification and then analog to digital conversion. So all of these can add noise, but what you really want is not to be affected so much by those. You want to actually be as little affected by all the instrumentation contribution of noise and be really dominated by the body noise, because that is something you cannot control. Okay. The only thing that we control is the system, right? But this we can't control. Um,
Does temperature have an effect on it? On SNR?
Absolutely. Yeah, so temperature. So this is all 4 KTR, right? So T is the temperature. And to be honest, if you think of a coil, we could, one of the ways to reduce the noise there is either to reduce the resistivity or to reduce the temperature. And in fact, there are cooled coils, like and also HTC coils, so high temperature superconducting coils. They do exist in order to get better signal to noise ratio when you're dominated by your system. We often use very low noise preamplifiers that injects very little noise, and our analog to digital converters use a lot of bits in order to avoid any quantization error, quantization noise. So really, it's the body that generates, and is of course also dominated by this, but one of the issues there is the T is very hard to control. I don't know about you, but most people are usually about 37 degrees Celsius, and it's very hard to cool them below that, or much below that, maybe 36, 35, that's getting kind of not very comfortable. And then after that, you're gonna kill. So probably not advised.
Yeah, I was just thinking like, cause like gradient heating and stuff like that with temperature, if that would.
So the gradient heating, yeah, no, that can increase the temperature, but usually increases the temperature of the gradient system, not the receiving system. So not necessarily going to have an effect. And you just disappeared. But I hope it was recorded. I hope. Okay, so I think I'm going to stop now here, and then we're going to continue next time. Okay, next time we're going to talk a little bit more about the model of coils and stuff, but then we are going to move very quickly in order to talk about the behavior of pretty much SNR in imaging. Okay, that's kind of where we're going to go. So from an instrumentation point of view, we're not going to go very deep, but we're going to analyze the imaging part very, very carefully. In particular, we're going to look at, scan time, readout time. We look at resolution and how those impact signal to noise ratio. All right, and we're going to do that on Tuesday. Remember, on Thursday we have a guest lecture. Shreyas Vasnawala is going to talk about clinical aspects of MRI from a radiologist's point of view. Right, so don't forget that. That's a highlight of the semester. And here's what I want to say. Recording has stopped. Come on, help me here. I can.